Okay, so we have talked about finding all the zeros of a polynomial function, but the one thing we've neglected to talk about so far are irrational zeros. Irrational zeros, recall that irrational numbers are numbers that cannot be expressed as a ratio of integers. So like 3 divided by 2, 3/2, that's a rational number. Something that would be irrational would be like the square root of 2, or the square root of 3, square root of 5, or pi, or any number that cannot be expressed as a fraction. And the reason that these come up is because if we can't factor something, if we can't use the rational zeros theorem and come up with a factor of something, then we're not able to get an exact answer. Um, Occasionally we are. Like if we have one or potentially up to one or more rational zeros and then a remainder, we have like a leftover quadratic that's not factorable, but we can solve it with a quadratic formula, then we can find those irrational zeros exactly using the quadratic formula. However, sometimes we just have no rational zeros whatsoever. And in that case, we don't have much to do. So here's an example like that. F of x is equal to x to the fourth minus x cubed minus 25x squared plus 3x plus 42. If you do the rational zeros theorem on this, you get that the list of possible rational zeros for this function is 1 plus or minus 1, 2, 3, 6, 7, 14, 21, and 42. Now, if you plug all of those in, you'll find that none of them are zeros. What we can see, however, is that there appears to be some change happening between positive and negative in this kind of range, right? We change signs in this area. Everything else here is positive, so these are all positive. Another way to look at this is if we arrange all of those possible inputs from smallest, like most negative, to most positive, we can see, all right, so at negative 42 we have a huge number, right? And then as we're getting down between negative 6 and negative 3, it goes from positive to negative. The outputs go from positive to negative. So what that tells me is that somewhere between negative 6 and negative 3 there is a 0. That's what the intermediate value theorem tells us. If f of negative 6 is a positive number and f of negative 3 is a negative number, that means that there must be at least one 0 between negative 6 and negative 3. Okay. We also know that there are 4 zeros for this polynomial. That's what the fundamental theorem of algebra says. And if we keep going here, we can see that there's another 0 between negative 2 and negative 1, because f of negative 2 is negative and f of negative 1 is positive. We know that f of 0 is 42, f of 1 is 20, f of 2 is negative 44, which means there's another 0 here between f of 1 and f of 2. And then f of 3 is negative 120, f of 6 is 240, so boom, there's another 0. So we have found, just by doing this and using kind of logic, that there's one 0 between negative 6 and negative 3, there's another 0 between negative 2 and negative 1, there's a third 0 between 1 and 2, and a fourth 0 between 3 and 6. Okay, graphically what this looks, and that's all 4 of my zeros, so they're all real, they're according to what we have here, they are not going to be rational, so they're going to be irrational zeros. And so let's look at what this would look like on a graph. Like at f of 3 sorry, I'm looking at f of negative 6 is positive, f of negative 3 is negative, so we're down here. So this came down somewhere like this. Okay, then it says between negative 2 and negative 1 there's a 0, so it had to come up and go back through the x-axis there. And then it crosses at 0, it's positive 42, so it's positive. And then at 1, between 1 and 2 there's a 0, so it has to come down somewhere between 1 and 2. And then between 3 and 6, so somewhere over here there's another 0. So the graph is looking like something like this. Now, how would we go about finding what these are without a calculator? Well, there is a way. It's just really horrible, and I don't recommend doing it, but I am going to explain really quickly what that would look like. If you know that there's a 0 between negative 2 and negative 1, what you would do is you'd take halfway between negative 2 and negative 1, so negative 1.5 or negative 3/2, and you'd see, okay, is that positive or negative? You would find, I can't remember what the answer is, but if you found that it was positive, then what you would do is you'd bisect the the part of the x-axis where we know it crosses. So we check it right in between -1/2 and -2. So we would have, sorry, -1.5 and -2. So we would check -1.75. And then if we evaluate it at -1.75 and we found that it was negative, that means between -1.75 and 1.5, -1.5, there's a 0. So we cut that in half, and we keep doing that until we got within some amount of precision. It's basically a binary search. We keep narrowing the search and checking, is it true or false. If it's false, then we look at the other half. If it's true, we look at that and we cut it in half, and then we do the same thing over and over again until we narrow it down. It's called the bisection method, and to be honest, it's kind of horrible. And so for that reason, we have we generally refer to calculators when it comes to this. So I'll show you how that works. We're going to look at this on Desmos and on a graphing calculator, so that you can see it done in both ways here. So on Desmos, I have Desmos up. It's really easy. If you just type the function in, when you click on the graph itself of the function, right away it highlights the important points, and critical points include local minimums and maximums, or relative minimums and maximums, and of course the intercepts, the x and y intercepts. So right away, boom, right there we found those are our irrational zeros. On a calculator, which it's a much more involved process, but calculators tend to be what you will have available. If we graph that, right, I type in the function and then we hit graph, we see this graph. Now this graph doesn't look like it's much of a graph. That's because the axes are set up wrong. If I change that, if I make the y minimum like -500 and the y maximum +500, and I'll change the y scale to like 100, then if I graph that, we're going to see something more reminiscent to what we see in Desmos there. Now, if I want to find the coordinate, the x value of these points, then what I have to do is find the zeros. So if you go second trace, which is the calculate button, you'll get the zeros. And then it wants me to pick a value to the left of one of the zeros. So this is a 0 to the left of it. I hit enter, and then if I go over to the right, find one on the right, and then it wants me to guess. So maybe like right there is a 0, and it comes up with my -4.37, which we can see is the same value that we have over here. And then we continue this process for all the remaining zeros. And so if we wanted to find this one, we're to the left of that one now, to the right of that one now. Then we guess there, and it gives me the output of -1.316, which is the same one we had here. And you just continue that process, and that's really the only way that we can accurately find the zeros. There's another way you can look at this, and that's on the table set part of the calculator. You would have to go and change the delta table, so the difference in each of your between each of your values here. This is not, I don't advise you doing this. You should really just use the trace part of the calculator, so like the calculation part to find the zeros, because this is just going to take a really long time. You'd have to keep scrolling until you found when we changed from positive to negative in the y values. So you can see this is going to be a pain here. It's going to happen after 1. So 1.37, we got to keep scrolling. 1.3, so went too far. So you can see right here between 1.37 and 1.38, we go from positive to negative. So that's an indicative that we have a 0 there. Then you drill down, and depending on what precision your teacher or the book or the problem is asking you to find, that's how you could do that. But again, it's much easier just to use the trace function. And then that's how you do that. So that's it, right? We've been able to find every possible 0. We found real zeros, irrational real zeros, we found non-real zeros, and now we have irrational zeros.